So in calculus, when you're looking at these series problems, you're going to be on the exam or on the quiz or whatever, and they're going to show you some formula that looks like this or like this, and maybe it's a nasty looking one, but the point is it'll give you some sigma notation, and they'll ask you, or maybe a bunch of them, they'll say which of these converge, which diverge, whatever. And then they won't usually tell you which test to use. On their homework, they'll say, hey, use the p-test or use the ratio test or whatever. But on the test, on the exam, they're just going to give you a bunch of them, and you'll have to figure out which test to use on which problem and that kind of thing. So that's why each of these videos in this chapter is about a different one of those scenarios. And the one we're talking about in this video is a p-series. So just a refresher, when we saw a geometric series, the giveaway or the tell that you were looking at a geometric series was that you had a number raised to an exponent of n. And you didn't have anything else, like there was no n factorial in there was no square root of, of n, anything like that. It was a constant raised to a power of n, either upstairs or downstairs or whatever. The giveaway for a p-series is the switcheroo. In the p-series, the power is an integer, or a number, just a constant, and then the n is raised to that power. So in this one, we have 1 over n squared, and we could also rewrite this particular one, just to make it look more confusingly like a geometric series. We could have written it as 1 over n squared, which is more like the standard way of writing it probably. So you'll see that what we have is, downstairs we've got an n to a constant exponent. So if you want to list out the terms of this series, it would be, so for this p-series we have here, if we plug in 1 for n, we just get 1 squared. Plug in 2 for n, you get 1/2 squared is 1/4. Plug in 3 for n, you get 1/3 squared, which is 1/9. So you can see the pattern here is we're just going to put all the perfect squares in the denominator. So not pretty exciting stuff. And it turns out the test for this is really simple. When you have a p-series, so you have n raised to an exponent, it converges if that power is bigger than 1. So it is kind of backwards. On the geometric series, remember the test was that the absolute value of r had to be less than 1. So we wanted ratios less than 1. Well, in this one, because the n is downstairs, we want a power bigger than 1. So 1 over n squared, we just did this one. That was the 1 over 1 plus 1/4. Just we had all the perfect squares downstairs. And what this is saying is this one converges because this number 2 is bigger than 1. Seems pretty straightforward. This series, we've got a power bigger than 1. We've got a power of 3. So that one should converge. And this is just going to be all the perfect cubes. I don't actually know what the next one above that is. Oh, 125. Anyway, so that's going to be a p-series. Not to be confused with a power series, which is something totally different. That'll be a different chapter. But a p-series is just when you have an n raised to an exponent, a constant exponent. By the way, 1 over n to the n would not be a p-series because sure we have n being raised to a power, but that power is not a constant. It's got an n in it, so that's not a p-series. So what about this one? Well, guess what? The power here is 1/2, and 1/2 is not less than 1, so this diverges. And if we listed out the terms, we'd still have 1 as our first term, but then we want to have 1 over root 2 plus 1 over root 3, which is really 1/2. And you kind of see this actually looks sort of like the harmonic series, except it's got square roots. Well, guess what? This last one, this is the harmonic series, 1 over n. So it's 1 plus 1/2 plus 1/3. So, interestingly, the harmonic series is a p-series with p equal to 1. So by the p-series test, does this one converge? No, it doesn't, because p has to be greater than 1 for a power series to converge. For this one, p equals 1, so it diverges. And we also already know that the harmonic series diverges. So if I was you, I would get really, always keep an eye out for whether the harmonic series is involved, because we're going to use it a lot. In the comparison test later, we use the harmonic series all the time. And just whenever you see the harmonic series, you can sort of throw everything else out the window. You don't need any tests. You just know the harmonic series diverges. So, good times. Harmonic series, p equals 1, p series diverges. All right, converge or diverge. So let me see. We're in the p series video, so these are probably p series, but we need to verify that. So I think what I should do is rewrite this formula in more of a p series way, because the square root is really a power of 1/2, right? So this is really the series from 1 to infinity of 1 over n to the 1/2. And now that I've got that written in sort of exponential form, we can see that, oh yeah, this is indeed n raised to a power, and that power is less than 1, so it diverges. What about this puppy? You can see this is very similar to the one above. So once again, I'm going to want to just rewrite it to look more officially like a p-series. So the way to do that is to first split this up in the square root of 3 over the square root of n. Because when you have a square root of a fraction, you can sort of make that two separate square roots above each other, no problem. And then once you got that, you can do square root of 3 over n to the 1/2. Just convert that root to a power of 1/2. And sure enough, p equals 1/2. So this diverges. Now there's going to be other situations in more advanced problems where you have a square root of n, but something converges anyway. But that's not a pure p-series. So this p-series test only applies when you've got n to a constant power, and that's all there is. There's no n factorials, there's no constants in front of the n, it's just an n to a power. So the two on this page are these power series, or the p-series rather. Well, they're in disguise. So what we need to do in this first one, you notice we have n to a power and then n to a power. We really want to reduce those, because algebraically we can cancel this, because that upstairs really n to the 1/2. So if you reduce these, you get 1 over n to the 3/2. And now you can see, yeah, this is a p-series with p equals 3/2. And the p-series test is if p is greater than 1, it converges. P is bigger than 1, so it converges. Alright, it's kind of a cool test, because if you know you're working with a p-series, then you can just look at whatever that exponent is, say whether it converges or diverges, and move on with your life. You don't even have to list out the terms if you don't want to, unless your teacher says, hey, list out all the terms. Alright, this last one, it might look a little tricky because we have an exponent within a square root, but really that's just rational exponents. So we can, upstairs we just have a root 3, and downstairs we have n cubed raised to the 1/2 power. So that's n to the 3/2 power. So we have n to the 3/2. That means that p equals 3/2 yet again, and therefore it converges. Alright, now you might be wondering, what about that square root of 3 upstairs? Well, it turns out that sigma notation, or series in general, they're kind of like integrals. If you have a constant, like the square root of 3, you can sort of just move that out front. So this is actually algebraically equivalent to the square root of 3 times sigma from n equals 1 to infinity of 1 over n to the 3/2. And you can see right here that if you just put a square root of 3 out front, if this thing diverges, square root of 3 times infinity is also infinity, so you're still a hose and it would diverge. And then of course if it converges, like this one we think converges by the p-series test because p equals 3/2. So if you think that this thing converges, whatever number it converges to, like 5 or 7 or 3/2 or whatever it converges to, if you take a finite number and then multiply it by square root of 3, you've still got a finite number. So having a constant out front, that will affect the sum. It'll affect what number we're approaching, but it won't turn a normal number into infinity or vice versa. So the constant out front does not affect convergence, and that's why having a root 3 up here doesn't really matter. The thing either converges or diverges based on the terms that have n's in them. So either the n downstairs or the n in the exponent, like we had with geometric series, it's the ends that get you, not the constants. The constants will mess with you a little bit, as we'll see in the slide after this one. So our harmonic series is a p-series, as I mentioned. Just want to keep drilling that because this is kind of a trick question. You know, the harmonic series, as I've said, pops up all the time, and then knowing it's a p-series might get you a trick question on a test. You know, it just depends. But the point is that this is really 1 over n. You can kind of just put a 1 there, right? Because any letter you want, or any number, you can just throw exponent of 1 onto it. It doesn't do anything. So that's how we know it's a p-series. And since p equals 1, that diverges. But again, you want to be so sharp with this that anytime you see 1 over n, you're just thinking, oops, that's a harmonic series. That diverges. You shouldn't even be thinking, oh, I wonder if that diverges. It should be like that fast. It's like, oh, harmonic series diverges. All right, so I mentioned before that square root of 3 upstairs does not matter. But what if you have a number in front of n, like down here? Or what about this one, where we added a plus 1 to n? Is this still a p-series? Well, it turns out it may or may not be. We have to actually list out some terms and see. So if we list out the terms of this thing, when n equals 1, we get 1/2, or 1 over root 2, I should say. When n equals 2, we get 1 over root 3. When n equals 3, we get 1 over root 4, which is 1/2, obviously, but I just want to leave it like this to show you the pattern. So you can see it's almost like the square root of the harmonic series, right? And isn't that the same series we would have gotten if we had done just a straight up p-series of 1 over square root of n? It is, right? It's really close. If we just switch from n equals 1 to n equals 2, it would be identical. So these are all the same terms, and therefore this really is a p-series. So, you know, if the only question on the test is, does this converge or diverge or whatever, or is this a p-series, then by listing out terms, you can show that it really is just a p-series. And if you wanted to, you could rewrite it like I did right here and just show, yeah, that's really just a straight up p-series with n to the 1/2, and then just start at n equals 2 instead of 1. But there's a property of series where if you just change the starting point, as long as at some point in the series, the terms all start matching up. So like, you know, so from 1 over root 2 to infinity, the terms are exactly the same for this series and this one. If we'd start at 1, for example, then they're basically either going to both diverge or both converge. If I threw a 1 plus in front of here, or if I threw a 5 on the front of this, that's not going to affect whether it goes to infinity or not. It'll affect the sum. I just made the sum 5 bigger, but I didn't make it infinity bigger. So that's why if you have two sequences or two series that match, like all their terms match all the way up to infinity, there's just maybe a couple are different at the beginning, you can kind of ignore the couple at the beginning when you're trying to test for convergence. So because this thing has this, the moral of the story is that because this sequence with the n plus 1 under the root has all the same terms going towards infinity as a pure p-series of 1 over root n, then they're both p-series, and since this is n to the 1/2, meaning p is 1/2, that means it diverges. So because we could find a p-series that had all this, almost all the exact same terms that does diverge, then therefore our original one diverges also. But look at this one down here. I don't think we'll be able to do that with this one, because if we list out the terms, we'll get, our first term is 1 over, let's see, plug in 1, so we get 3. Plug in 2, you get 5. So you can see on this one, we're getting the square roots of just the odd numbers downstairs. And I'm not sure about that one. That's not a pure p-series, right? A pure p-series, you go 2, 3, 4, 5. All the integers are represented. But by throwing that 2 in front of things, that messed it up. There's no sort of standard p-series that we can find that'll exactly match these terms, because we're missing the root 2 term, we're missing the root 4 term, missing the root 6, the root 8, the root 10, the root 12. We're missing all those terms, so it's not an exact match, and therefore we can't really say by the p-series test whether this one converges or diverges. It turns out, though, that for situations like this, where we're pretty sure it's basically a p-series but just a little bit off, We're going to have some tests for that, like the comparison test, the limit comparison test, the ratio test, some things like that where, if you have something that looks an awful lot like a power series or a P series, sorry, not a power series, a P series. If you have something that looks an awful lot like a P series, or it looks a lot like a geometric series but isn't quite a geometric series, we'll have these more advanced tests to figure out, well, hey, it's close enough that we can sort of say they both diverge or whatever. And we'll cover those in the upcoming videos. But as far as if something's, if you want to use the P-series test on this bottom one, you can't use the P-series test directly because it's not a pure P-series. So we don't know what P is. All right, so stick around for some of those more advanced comparison techniques coming up.